All right, let's talk about section 9.2. Talk about series and convergence. In the previous section, we talked about a sequence, which is a function from the natural numbers into the real numbers. And although that is a formal definition, oftentimes it can be thought of as a list, an ordered list of numbers, where there is a first term, a second term, a third term, and the order of those is set. Now, once we have a sequence, one of the things we could do to it is we could add the terms of that sequence. So, if I have the sequence that's given by a sub n is equal to a sub 1, comma, a sub 2, comma, a sub 3, comma, dot, 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 comma, a sub n, comma, dot, dot, dot. That is an infinite sequence. Just like that. Now, if I were to take these terms and add them together, well, then that would be the sum of the a sub n terms. It would be the sum of the first term, the second term, the third term, all the way up to the nth term and beyond. So here, this would be the sum as n goes from 1 up to, and we say, well, there is no end to this. They keep going. So here, n goes from 1 to 2 to 3 to infinity. And of course, this would just be the sum of the first term with the second term, with the third term, with the fourth, fifth, all the way up to the nth term. But this doesn't stop. This keeps going. This is called a series. Now, in some books, they make the distinction of calling this an infinite series, mostly because, well, you could define a finite series. You could define a series where you have a set of terms that eventually ends. So you could have just the sum of the first three terms. Likewise, you could have a sequence that is finite. You could just have a sequence made up of three terms. And those are both definable. You can define finite sequences and finite series. But for the purposes of this class, all of the sequences and series, and certainly the ones in this section and in this chapter, we're going to be looking at are infinite. So when we say series, you can assume we mean an infinite series. If there's ever an instance when we have a series that has a beginning or an end, we will explicitly make that known. If we just say a series, you can assume that we mean an infinite series. But, I mean, how do you do that? I mean, look, you're adding together an infinite number of terms. Well, surely that must be infinite. Well, if you think that, then you haven't been paying attention for the last 2 semesters. Because after all, we've added infinite number of things before and gotten finite amounts of, gotten finite values. After all, if you go back to the end of chapter 8, when we talked about the improper integral, we saw integrals from 1 to infinity or from 0 to infinity, and those sometimes diverged. Sometimes they gave us an infinite result. But other times, you just got the number 5, or the number 2, or the number 4 pi, or whatever you might have gotten. So, just because you have an infinite number of terms added together does not mean that you're going to have an infinite value. But maybe you will. So, in this section, we're going to talk about the difference between those, and throughout the chapter, we're going to learn a bunch of different tests to see, given any series, can we figure out, first of all, can we figure out if it does converge? And if it does converge, can we figure out what it converges to? You're going to find that the answer to the first question is a lot easier than the second one. Can we find if a sequence converges? A series. Can we find if a series converges? The answer is not always, but often yes, we can. The second question, okay, once we know it converges, do we know what it converges to? That's a much harder question. We won't always be able to do that. So we'll see what to do, what we can do, what we cannot, and when we can't, we'll see what we'll do in those instances. So let's talk about generically, without any specific numbers, how could we interpret this? What would it mean for this to add up to a finite amount? You say, well, easy. Once I added them all together, I should get a number. Well, how can you add them all together, though? I mean, if this is an infinite number of terms, you pull out your calculator and type in the first term and the second term and the third term. And let's say my terms are 1 plus 1/2 plus 1/3. Just Okay, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus, when do I stop? Well, never. You're going to keep going forever. So even if that does converge, how would I ever know? I'm never going to get to the last one because there is no last one. Okay, so how could I possibly do this? If I'm not adding an infinite number of terms, then how am I ever going to know what an infinite number of terms adds to? Well, we don't add them all together at once. We add some of them and start to look for a pattern. So these are called the partial sums. We're not going to add the entire thing. We're going to define a set of partial sums. So let's see, partial sums. Given this sequence, given this series, S sub 1 is just the sum as n goes from 1 up to 1 of a sub n. Or in other words, it's just that very first term. S sub 1 is just the same as a sub 1. S sub 2 is going to be the sum as n goes from 1 up to 2 of a sub n, which is a sub 1, and you're going to keep counting until you get to a sub 2, and you're going to add those together. And S3 is going to be the sum as n goes from 1 up to 3 of a sub n. So that'll be a sub 1, and then we're going to count up a sub 2, and then we're going to count up until we get to 3. So it's going to be a sub 3, and then we're going to add those all together. So a sub something is the sum of the first something terms. Here, we can take S sub n as being the sum as, and here we'll use a capital N to distinguish it from that little n, as little n goes from 1 up to capital N of a sub little n. Or in other words, it's a sub 1 plus a sub 2 plus a sub 3 plus all the way until you get to a sub n. Now, the nice thing about these sums is that these are finite sums. All right? So, these, we couldn't possibly ever add up all the terms. Even if it does converge to something, we'd never finish. These are finite. Maybe it'll take you a few seconds or a few minutes or a few hours, but eventually you could add all of these terms. Okay, so what? Well, once you add these terms, these are going to be numbers. Maybe we can find a pattern to these numbers. So this brings us to a definition. We're going to formally now define what we've informally said up here. So let the sum as n goes from 1 to infinity of a sub n be a series. We don't know what kind of series, we don't know what these terms are, but it doesn't matter. Here we're defining this in the most general sense. You have a series. Let's define the partial sums. Here the nth partial sum of the series is given by the sum as n goes from 1 up to capital N of a sub little n, which is given by a sub 1 plus a sub 2 plus a sub 3 plus ... plus a sub n. And notice that does have an end. So here, this is finite. It ends eventually. Now, out of these partial sums, we're going to make a sequence. Not a series. We're not going to add them together. We're just going to form a list. So now, let S sub n written this way be the sequence, not a series, but the sequence of partial sums. All right. Then, if the limit as capital N approaches infinity of S sub n is equal to some real number L, where L is a real number, then the sum as little n goes from 1 to infinity of a sub little n, in other words, the series, is said to converge to L. Okay. So here we're defining what it means for a sequence to converge. Okay. Here we're also defining what the nth partial sum is. And here we're defining what the sequence of partial sums is. So to best go through all the finer points of this definition, let's take a look at an example. And we're going to look at the canonical example. This is the same example that I saw when I was a student. And it's the same example that my professor saw when he was a student. And it's the same example that every student sees because it is the first example that is accessible, that is simple, but that uses all of this. There is a very common example which is used, not because it is the most important example in the world, but because it is the simplest one that covers everything you need. So here, consider the series given by the sum as n goes from 1 to infinity of 1 over 2 to the power n. And here the question is, find the sum. Here, the question itself kind of assumes that the sum is defined. In other words, it assumes that this actually has an answer. It assumes that it converges to a number. Note that that won't always be true. Sometimes, if the question is find the sum, the correct answer is the sum is undefined, or this sum is infinite, or this diverges. Sometimes the answer to find the sum is I can't. There isn't one. But here, this one will work out really rather nicely. So to find the sum, by definition, what we want to do is we want to define the partial sums. Okay, so let's talk about those first. The partial sums. Okay, well, the partial sums are going to be s sub 1, s sub 2, s sub 3, s sub 4, and so on. Okay, well remember, s sub 1 is just the very first term of this sum. Okay, well let's see, well what are the terms of this sum? Okay, well that's, if n is equal to 1, that's 1 over 2 to the 1, which is a half. Plus, if n is equal to 2, that's 1 over 2 to the second. Okay, that's 1 over 4. And if n is equal to 3, that's 1 over 2 to the 1 over 2 to the third, which is 1 over 8. And then for 4, that's 1 over 16. And then 1 over 32, and so forth and so on. Now, of course, if you grab one of these things and start punching things in, you'll never finish, because, of course, these never finish. But right here, these are a finite sum, which means I could just grab a calculator. Or in fact, these are small enough, I could just do them by hand. S sub 1 is just the first term. S sub 2 is the sum of the first two terms. 1/2 plus 1/4, that's 3/4. Okay. S sub 3, that's the sum of the first three terms. 1/2 plus 1/4 plus 1/8. And if I add those together, that's 7/8. Okay. And S4, that's going to be 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, which is 7/8 plus 1/16, and that's going to give us 15 over 16, like that. And let me do one more just because I can. If I add together the first 5 terms, well, that's going to be 15/16, right? These first 4 are the 15/16. But then we're going to add one more term, which is 1 over 32, which is going to give me, what is that, 30 over 32 plus 1 over 32, that's 31 over 32. And of course, that does keep on going. We have more partial sums. But that's going to be good enough. because now consider the sequence of partial sums. In other words, I'm going to take this S1, S2, S3, S4, S5, and I am just going to set them up in a list. And I'm going to put them in order because there is a first one, a second one, a third one, a fourth one, a fifth one, and so forth. Just like that. Okay, but now I have those numbers, so that's equal to, and I can just write that down. That's equal to 1/2, 3/4, 7/8, 15/16, and 31/32, 30 halves? I'm not sure how to say that. 31/32, comma, dot, dot, dot. Oh, but look, I recognize those denominators. They're 2 to the n power. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. Oh, and I recognize the numerators. They're just 1 less than the denominator. So here, I could write this sequence. Instead of writing it term by term, I could just write it using its nth term. This is the sequence that's made up of, well, let's see. The denominator is 2 to the power n. And the numerator is the same as the denominator minus 1. Right? 4 minus 1, 8 minus 1, 16 minus 1. So that's the same as the denominator minus 1. Okay? So I started with an infinite sum. I broke it up into partial sums, and from those partial sums, I made a sequence. That sequence can be written using its nth term. And wow, that is the ugliest brace I have ever drawn. All right, let's try. There we go. Yeah, that's not really any better, but oh well. But now consider the limit of this sequence. So now let's take a look at the limit of the sequence of partial sums. After all, this doesn't end. There are more partial sums. Well, okay, so what happens as I take the 6th one, 7th one, 10th one, millionth one, billionth one? Well, what happens is that as I let n grow? Well, then I'm going to take the limit of this. So I want to take the limit as n approaches infinity of 2 to the power n minus 1 over 2 to the power n. Okay, but now I could rewrite this. I could divide the top and bottom by 2 to the power n. We're back in Cal 1. We're dividing out by the biggest powered term. So this will give me 1 minus 2, this will give us 1 minus 1 over 2 to the power n over 1. All I did was I divide everything in the numerator and everything in the denominator by 2 to the power n. That makes that 1. That makes that 1. And then minus 1 gets divided by 2 to the power n. But now as n approaches infinity, this drops off to 0. As n approaches infinity, this goes to 0. So I'm left with just 1 over 1, which is the number 1. But by our definition, if the limit of the partial sums is equal to L, and as long as L is a real number, doesn't matter what it is, then we say that the infinite series converges to that L. So here, we found that the limit of the sequence of partial sums is equal to 1. So by definition, by the definition of what the sum of an infinite series is, that means that the sum as as n, some books use I, some books use n, and you'll see me flip back and forth between the two. It's just a force of habit. The sum as n goes from 1 up to infinity of 1 over 2 to the n. That was our original problem. That's going to equal to the limit of the partial sums, which is equal to 1. And so our series converges. Ain't that strange? We have an infinite number of terms which we've added together, and we've managed to successfully add an infinite number of terms in a finite amount of time. Here, this took us 10 10 minutes, 5 minutes, something like that. I don't know. I didn't time it, but we did it in a finite amount of time. It did not take us to the end of time to pull that off. Here, this has a bit of a geometric interpretation. You can draw this out. Imagine that we are adding together volumes. So let's say I have a box here, and let's say it's a cubic, let's say it's a cube, but I'm not going to draw a cube because drawing in 3D is hard, and I'm not going to do it. All right, let's say I had this is got enough space in it to put exactly 1 gallon of water. And once I have more than a gallon, it's going to overflow. Okay, so now I'm going to fill it with water in stages. I'm going to fill it with, first of all, 1/2 of a gallon of water. Okay. Now I'm going to fill it with a quarter. Well, notice a quarter is 1/2 of a half, that means half of the remaining space will be filled. Now here I have some magic water, or maybe I have some ice, because I'm going to go ahead and fill it, and I'm going to say, okay, that's half of the remaining space. Normally you'd say, okay, well, water fills from the bottom up, but again, just as a visual, I have some magic water here. Okay, well, now I'm going to add 1/8 of a gallon. Well, notice I have a quarter, that's my empty space, and 1/8 is half of that. Okay, so that's half. But now 1/16 is half of that empty space. And 1/32 is half of that empty space. And the next one would be 1/64, but that's half of that empty space. So what this does is every time you're going to add a little bit more, it's going to fill in half of the remaining space. But if you're always filling in half of the remaining space, you're never going to really fill that up. Well, yeah, but the amount of empty space is getting smaller and smaller and smaller until eventually, when you add an infinite number of terms, it'll top off to give you the 1 full gallon. Now, of course, in reality, that's not a physical reality. In real life, drops of water take up a certain amount of volume, and there's only so small that your volume can get. The smallest drop of water will eventually be bigger than any of these numbers. So here, as a physical reality, that couldn't happen. But numerically, this works out to be exactly 1, as we see here. Now, this example is actually somewhat rare, which is one of the reasons why it is the canonical example. It's the first one that you really ever see. The thing that's rare about this one is that you get an answer. You say, you don't expect to get an answer? Well, we don't expect to get a numerical answer. Oftentimes, the best we can hope for a series is to confirm that it converges. If you know that it converges, it can sometimes be very difficult to figure out what it converges to. So in the coming sections of the chapter, you'll note that many times we're not even going to try to find what something converges to. It's sufficient to know that it converges. Once you know that it converges, you can say, okay, well now I'll grab a computer and I'll let it add up the first trillion terms. And that'll be a good estimate to what it converges to. And you say, well, why don't you just always do that? Well, because if it doesn't converge, if it diverges, well then if I add up the first trillion terms, well, that doesn't do us any good because this was going to diverge anyway. The first trillion terms tell us nothing. So oftentimes, what you do is you test, does this converge? If it does not, well then it doesn't. That's it, you're done. If it does converge, if you're lucky, you can find what it converges to. But in practical matters, oftentimes, once you find it converges, you plug this into a computer and let it compute the first trillion terms and say, okay, that's good enough. That's approximately what my sum is. And if it's not exactly right, well, it's close enough. All right. So in this section, let's take a look at a couple more examples of very rare problems, the kinds where you actually can figure out what it converges to. As our next example, let's take a look at what's called a telescoping series. Now, visually, these take on a few different forms, but when you start writing out the terms, the forms always look the same, regardless of what the original series might have looked like. So let's consider the sum. So example, find the sum, and this will be one of those cases where we actually can. Find the sum as n goes from 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. This is called the telescoping series. Why it's called a telescoping series, it will become apparent once we write out some terms. All right. One thing you might be tempted to do is to combine these, find a common denominator and do that. Don't do that here. And you say, is that wrong? No, it won't be wrong, but it's going to be a little bit counterproductive because a telescoping series is best seen whenever you have sums or differences of several terms. Once this is condensed down, it's still a telescoping series, but it just doesn't look quite as obvious. So here, consider the first few terms. If n is equal to 1, that's 1 over 2 minus 1 over 3. Okay, cool. Plus, well now the next one will be if n is equal to 2, that's 1 over 3 minus 1 over 4. Okay, plus. Now if n is equal to 4, no, I'm sorry, I'm at the third one. If n is equal to 3, that's 1 over 4 minus 1 over 3 plus 2, that's 5. Plus, let's see here, that's going to be the fourth term, so that's 1 over 4 plus 1, that's 1 over 5, minus 4 plus 2, that's 1 over 6. You see what happens? Look what happens to every other term. What's minus 1/3 plus 1/3? Well, that's 0. And what's minus 1/4 plus 1/4? Well, that's also 0. And what is minus 1/5 plus 1/5? Well, that's also 0. Notice that the 1/2 and the minus 1/6 are the only ones left. And you say, oh, well, then I combine those. Well, no, because remember, this keeps going. So if I kept this going, the next term would be 1 over 6 minus 1 over 7. And you'd say, okay, so then those cancel. Well, yeah, but then if I keep going, that's going to be 1 over 7 minus 1 over 8. Oh, and then that means these go away. Well, notice, every time I add another term, the next term disappears on me. Okay, so that means this is the only one that's ever left. All the other ones go away. Notice this term right here is getting smaller and smaller. The only uncanceled term over here was 1 over 6. Then it was 1 over 7. Then it was 1 over 8, and so forth and so on. As a matter of fact, well, let's see. If I only had one term, 2 terms, 3, if I had 4 terms, the uncanceled term was 1 over 6. If I had 5 terms, the uncanceled term was 1 over 7. And if I had 6 terms, the uncanceled term is 1 over 8. Well, that's just the number of terms I have plus 2 is my denominator. So what that suggests is that the nth partial sum is going to be 1/2, because notice that one's always there, plus my numerators, oh sorry, I guess that should be a minus, because the leftover term is always a negative. So minus 1 over, and then it's the number of terms I've done, 1, 2, 3, 4, 5, 6. If I add 2 to that, that's my denominator. So the number of terms plus 2. So this is my nth partial sum. Okay. Incidentally, the name telescoping series, you see that it keeps expanding out. The first term stays the same. Sometimes it'll be the first 2 or 3 terms stay the same. But after that, all the other ones sort of cancel out, and that very last one keeps shrinking. At this point, you might already see where this is going. All of this is going to go away. This last one will become so small it won't matter, and that's what it's going to be. That's what's going to be left. But here, let's be formal about it. If I take the limit as capital N approaches infinity of 1 over 2 minus 1 over n plus 2, as capital N approaches infinity, 1 over capital N plus 2 will approach 0. So this thing right here is 0. That's constant, so it's not affected. And so the limit of the partial sums is 1/2 minus 0, which is 1/2. So here, that means that the sum of the telescoping series is 1/2. All right, now let's take a look at the next type of series, and that's a geometric series. Now, you have noticed that up to now, all of our series begin at n equals 1 to infinity, and that's going to usually be the case. However, the geometric series is, well, special in a few different ways. To begin with, this one begins with n equals to 0. So you have well, what's often called the 0th term, as opposed to the first, second, third term, and so forth. Here, this is just one extra term. It's not anything that's going to change the fact that you still have an infinite series. But by having that extra term, we end up getting a much nicer result than we otherwise might have. So the geometric series is the sum as n goes from 0 to infinity of a r to the n. So we start off with n equals to 0. So a r to the 0. Well, r to the 0 is just 1. So that just leaves us a. And if n is equal to 1, we get ar to the first, and then ar to the second, ar to the third, fourth, fifth, and so forth. Eventually you get to ar to the n, but of course, this being an infinite series, this keeps on going forever. All right, so once you have a geometric series, you have a theorem. Ooh, that should be a 0. Our theorem says, okay, let the sum n go from 0 to infinity of ar to the n be a geometric series. The series diverges if r is greater than or equal to 1. However, if r is between 1 and 0, an absolute value, then that means the series converges. And not only do we know that it converges, we actually know that it converges to a over 1 minus r. This is a rare case of we not only know that the series converges, but we also know conclusively what it converges to. And here it converges to actually a very nice number. All right, so let's see why that should be. So our proof will give us a reason why our theorem should be true, but it'll also help us go over more about how sequences and series relate and how we use the sequence of partial sums to talk about what happens to the series. So first of all, let's begin with a geometric series. Consider the geometric series sum as n goes from 0 to infinity of a r to the n, where r, an absolute value, is between. Actually, let's not even consider the separate cases. Let's just consider the geometric series with r not equal to 0. That's the only thing we want to start off with. And the only reason we want to start off with this one is because, well, if r is equal to 0, 0 to a power is 0. And then anything times 0 is also 0. So here, this isn't a geometric series. It's just 0. 0 plus 0 plus 0. So here, we don't want to consider r equals to 0. So let's consider this as long as r is not equal to 0. Okay, well, if r is not equal to 0, then we have to consider the partial sums. Because after all, that's the only way we could ever hope to find this sum. Here, I'm going to call this series S for series, and it'll just work as a shorthand notation later when we start writing out our results. Okay, so here, I'm going to take the partial sum, consider the nth partial sum S sub n. Well, that's going to be a plus ar plus ar squared plus dot 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 plus ar to the power n. Oops, ar to the power n. And of course, that's just how a geometric series is defined. And here we're just going to cut it off at the nth term. None of that extra stuff beyond that. ar to the n. Okay, so now let's note that this is just a regular sum, which means it's a finite amount, it's a finite number. So this is just a regular equation that you might see in an algebra class, which means I can manipulate it the same way I usually manipulate an equation. Whatever I do to one side, it's perfectly valid as long as I do the same thing on the other side. Now notice here, r is not equal to 0, so if I multiply both sides by 0, I get a number that's non-zero. So that's going to give me r times s sub n is equal to r times a plus ar plus ar squared plus dot 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 plus AR to the power n. Well, notice I can distribute that R all the way out. So that's going to give me RS sub n is equal to AR plus AR squared once I distribute there. And then the next one will be AR to the third, fourth, fifth, and so forth until I get to AR to the power n. Oh, but notice there's one more. That very last one, if I multiply it by another R, the power goes up by 1. So that's AR to the power n plus 1. Okay, so now consider what happens if I subtract these two. If I take S sub n minus R times S sub n, that's going to give me all of this stuff, A plus AR plus AR squared plus dot 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 plus AR to the n minus all of this stuff, which is AR plus AR squared plus, there's a bunch of stuff in here, plus AR to the n. Oh, but there's one more. So plus AR to the n plus 1. But notice, most of these terms subtract away. AR minus AR. AR squared minus AR squared. All of these in the middle are going to subtract away. And finally, AR to the n minus AR to the n are going to subtract away. All of these numbers subtract away. Well, except for the first one and the last one. So I'm left with a much simpler expression. S sub n minus RS sub n is equal to A minus, all of this stuff is gone, minus AR to the n plus 1. Notice here I have a common factor of A. Notice here I have a common factor of S sub n. Now remember, S sub n is just a number. It's a sum of some terms. So I can factor it out. So I can write this as S sub n times 1 minus R equals A times 1 minus R to the n plus 1. Now, if I know things about S sub n, in particular if I know that it converges, that'll be enough to tell me that this converges. So the partial sums are what I'm really interested in if I'm trying to figure out what happens to my series. So let's go ahead and divide both sides by this thing, by 1 minus R, to isolate my S sub n. So here this will give me S sub n equals A times 1 minus R to the n plus 1 over 1 minus R. Well, notice now that if R is equal to 1, we have a major problem. If R is equal to 1, this whole thing is undefined. So if R equals to 1, then that means S sub n is undefined. Oh, but if S sub n is undefined, then that means that its limit is undefined. So the limit as n approaches infinity of S sub n is undefined. Oh, well, if that's undefined, then that means that the series is undefined. So that means S diverges. Okay, so we know what happens when R is equal to 1. The whole thing's nonsense. But what if R is not equal to 1? Well, then there's two possibilities. What happens if R is less than 1 in absolute value here? Oh, I suppose before I say that, I should talk about what happens if R is equal to negative 1. After all, we are talking absolute value here. If R equals to negative 1, we can go back all the way to the very beginning. If R is equal to negative 1, notice that's A plus negative A. But now negative 1 squared, that's positive 1. So notice the R's, if it's negative 1, it's going to be A, negative A, negative A, negative A. But when I add together a and negative a and a and negative a, I'm going to get, well, I'm going to start with a, then I'm going to have 0, and then another a, and then 0 again. Every other term will cancel out. So if r is equal to negative 1, here, these will oscillate back and forth. So if r is equal to minus 1, the sequence, there we go. The sequence of s sub n's is equal to a, comma 0, comma a, comma 0, comma a, comma 0, comma dot dot dot, which oscillates, and so it does not converge. Oh, how do you spell oscillate? I'm thinking, oh, I think I'm missing an S. Okay, so that's O-S-C. There we go. That looks a little better. Oscillate. And so diverges. If it oscillates, it'll never converge down to any one number, so it must diverge. Okay, so here we know R cannot be 1 or minus 1, or in other words, its absolute value can't be minus 1. So so if R in absolute value is equal to 1, S diverges. Okay, so if R equals to 1 or if R equals to negative 1, that means S diverges. Another way to say that succinctly is the absolute value of R is equal to 1, S diverges. Okay, so if that's the case, what happens if the absolute value of R is not 1? Well, there's two ways for that to happen. Either it's greater than 1 or it's less than 1. So let's see here. If the absolute value of R is less than 1, now here we still need this to be greater than 0 because again, it was if R is equal to 0, the whole thing just falls apart at the very beginning. So if the absolute value of R is between 0 and 1, then consider the limit of your partial sums. Since S sub n is equal to a times 1 minus r to the n plus 1 over 1 minus r, then the limit as n approaches infinity of your partial sums will be the limit as n approaches infinity of a times 1 minus r to the n plus 1 over 1 minus r. Now notice, n approaching infinity, capital N, as n approaches infinity, these are not affected. A, 1, and r, those are constants. So let's not worry about those. So let me write this a little bit separated. I'm going to write this as a over 1 minus r times 1 minus r to the n plus 1, like that. But now, out of focus here. There we go, that's a little better. So now, if r is less than 1, then you have a number that is less than 1 who you are raising to an infinite power. But as we remember from Calculus 1, if you take a number that's less than 1 and you're raising it to an infinite power, that's going to drop to 0. So this thing right here goes to 0. So we're left with a over 1 minus r times 1, which is just going to be a over 1 minus r. If that's 1 and that's 0, this whole thing is 1. And 1 times a over 1 minus r is a over 1 minus r. So there we go. If the absolute value of r is between 0 and 1, then my series will converge. Okay, but so now we see that it diverges if the absolute value is equal to 1. We see it converges if the absolute value is between 0 and 1. Finally, the last case is what happens if r is in absolute value greater than 1. Well, then let's consider the limit as n approaches infinity of our series S sub n, which is equal to the limit as n approaches infinity of, and again, I'm going to do the same kind of thing here. Well, actually, no, I'm not. I'm just going to write this as a times 1 minus r to the power n plus 1 over 1 minus r, like this. Here, we can divide these out. You may remember from your college algebra that you have, when you have the quotient of things like x to the power 3 minus 1 over x minus 1, x minus 1 is a factor of this, which means that it will divide out into this. The remaining term is a polynomial. Now, you may not remember exactly what that polynomial is in general, so here, let me remind you. Here, that's going to be, you may have, I'm sure you've seen it for the second power and for the third power. You may not have ever seen it for something bigger. So here, let's see what that looks like. If you have x to the second minus 1, that's equal to x minus 1 times x plus 1. If you have x to the third minus 1, well, then that's x minus 1 times x squared plus x plus 1. All right? This pattern actually continues on indefinitely. If you have x to the 4 minus 1, that'll be x minus 1 times x to the 3 plus x to the 2 plus x to the 1 plus 1. In general, if you have x to the power n minus 1, that's going to equal to x minus 1 times, well, here, that's going to be x to the power n minus 1 plus x to the power n minus 2 plus ... all the way till you get down to x and then 1. In general, that holds. I'm sure you've seen these. We do these in college algebra, and in general, this pattern holds. Here, notice that that's just that done in reverse. So here, that's instead of something to a power minus 1, this is 1 minus something to a power. So here, this whole thing is just multiplied by negative 1 to give us this. So if you wanted to flip these, you would just multiply both sides by negative 1. If you have 1 minus x to the power n, that's going to be 1 minus x times, and again, all this remains the same. If you multiply by negative 1, once you flip this one remains unaffected. Like that. So here, this becomes the limit as n approaches infinity of a times, well, let's see, that's going to be, I'm going to take 1 minus r times, now take the biggest power and subtract 1, and now subtract 1 again from the power, and then again and again and again, until you get down to r squared, and then r, and then 1. Just like that. And then, of course, that whole thing is divided by 1 minus r. Oh, but look, those two divide away, there and there. And now we're left with just a polynomial. All right? So here that's going to equal to the limit as n approaches infinity of a to the, a times r to the n plus r to the n minus 1 plus ... plus r2 plus r1 plus 1. Well, notice that's a polynomial. And if you have these numbers greater than 1 in absolute value, then as n approaches infinity, this biggest term will oscillate back and forth from positive infinite to negatively infinite, right? If it's if this is greater than 1, then this will grow to infinity. If this is less than negative 1, well, then that's still a big number that's oscillating back and forth because it has a negative that's being raised to a second power, third power, fourth power, fifth power, back and forth. In other words, this is a polynomial. And since this number is bigger than 1, as this grows, the whole thing will grow. And either it'll oscillate or it won't, but it doesn't matter. This will not converge to any particular number. So here, this thing goes off to infinity, which means it diverges. So because the limit of the partial sums converges, that means S must converge. Oh, sorry, must diverge. It diverges. It goes off to infinity. So that concludes our proof. We find that for a geometric series, if your R in absolute values between 0 and 1, you get convergence to this number. Otherwise, if the absolute value is greater than 1, or if the absolute value is equal to 1, you get that the whole thing diverges. And so that concludes our proof, namely, if your absolute value is greater than or equal to 1, the whole thing diverges, but when it's between 0 and 1, it converges to A over 1 minus R, just as we see right here. All right. So that concludes our proof. The proof of that may be a bit involved, but it is worth it because it does give us one of the nicest it does give us one of the nicest series possible. The geometric series is very nice, simple, and easy to work with. For example, find the sum of the convergence sequence of the geometric series the sum as n goes from 0 to infinity of 2 times 2/3 to the power n. Okay, so first of all, this A is 2 right here. R is the one that's being raised to a power, so that's got to be 2/3, just like that. And so first of all, if this in absolute value is less than 1, then you know it'll converge. Otherwise, it'll diverge. So here the absolute value of R is equal to the absolute value of 2/3, which is in fact less than 1, but greater than 0. So yes, this will converge. And that's all you need to know. As long as this number is between -1 and 1, as long as this number is less than 1 but greater than 0 in absolute value, then this whole thing will converge. And once you know it converges, you automatically know what it converges to. It'll converge to A over 1 minus R. Here you can write that as 2 over, well, let's see, 1 minus 2/3, that's 1/3. But dividing by a fraction is the same as multiplying by a reciprocal. So dividing by 1/3 is the same as multiplying by 3, which will give us 6. And there we go. That infinite series is equal to 6. Now you might think that's a little bit limited. It has to start at 0 to infinity. But of course, it can start somewhere else. Because after all, let's say the question was to find the sum. The sum n goes from 2 to infinity of, let's say, 3 times 1/4 to the n power. Okay, here this will only equal to A over 1 minus R if you start from 0. Oh yeah, but consider the fact that the sum as n goes from 0 to infinity of 3 times 1/4 to the n is equal to, well, let's see. If I take the first term and then the second term and I add those together, or I guess not the first and the second, but the 0th and the first term. So if I start from n equals to 0 up to 1 of 3 times 1 over 4 to the n, plus the sum as n goes from 2 to infinity of 3 times 1/4 to the n, that adds up to the same thing. Because after all, that's going to be 0 and then 1, and then this one will pick up at 2, 3, 4, 5, 6, 7, all the way out to infinity. So this one will be easy to find because this one is the geometric series that I can find using this formula, A over 1 minus R. This one is easy to find because it's finite. I just have a couple of terms to add. So let's go ahead and do that. This one is going to be, well, let's see. Here's my R, which I know is 1/4, so it is less than 1 in absolute value. So I know this will converge. All right, and since I know it will converge, I know it will converge to A over 1 minus R. And that's it. I know what that's going to equal. This is just the sum of the first two terms, right? If I take n is equal to 0, that's going to be 3 times 1/4 to the 0 plus, well, now n is equal to 1. That's 3 times 1/4 to the first power plus this, I don't know what it is. In fact, that's what I'm looking for. That was my question. So I need n goes from 2 to infinity of 3 to the 1/4 to the n. But notice, I know these. 1 minus 1/4 is 3/4. And if I take 3 and divide it by 3/4, if I take 3 and divide it by 3/4, that's the same as 3 times 4/3. Or in other words, it's just the number 4. That's just the number 4. Meanwhile, 1/4 to the power 0, that's 1. 1 times 3 is 3. Here, 3 times 1/4 to the first power, well, that's 3/4, plus this thing that I don't know. And now these, I can subtract over to this side. So that's 3 3/4. Let me subtract 3 3/4 from both sides. That's gone. Minus 3 3/4. And so 4 minus 3 3/4, that is just 1/4. And so that has to be the sum as n goes from 2 to infinity of 3 times 1 over 4 to the n. Which shows us that the geometric series is easiest when you go from 0 to infinity. But you can go from any number to infinity for a geometric series, because all you have to do is cut off the first few terms. If you start from 2 to infinity, cut off the first 2 terms. If you go from 5 to infinity, we cut off the first 5 terms. This is easiest when you start at 0, but if you have to start somewhere else, that's fine. Just cut off the first few terms that you don't need, and whatever's left, that must be your answer. So that's 1/4. This leads us to a really unexpected consequence of the geometric series, but it shows you why something you've been told is true for many, many years. It shows you why it's true and how to get that. One thing that you've seen going back to just basic arithmetic is one way of expressing a fraction is to write it out as a decimal. And you're told that every time you have a fraction, when you write it as a decimal, it'll either terminate or it'll repeat. And, well, okay, sure, I guess, but I mean, how do you get that? How do you know that it's going to be repeating? How do you know that every repeating fraction can be written as every repeating decimal can be written as a fraction? And if it could, how would you even do that? So example, this is sort of an interesting numerical consequence of these theorems. Consider the repeated decimal 0.363636 ... Right? The 36 repeats on forever. Go ahead and write that as a fraction. You say, how am I going to do that? Well, consider the fact that these are all the sums of fractions themselves. And say what now? Well, this is, if you ignore all the rest of this stuff, 0.36. We say 0.36 because it's easier to say, but that's not the right name for that number. That number is 36 hundredths because it's literally 36 hundredths. Okay, but now if these weren't there and it was just 0.0036, well, again, that's not the right name. 0.0036 is actually 36 10,000ths. Like that. And if these were all zeros, well, then the next one would be 36. Let's see, that's one like that. So that would be 36 millionths, and so forth and so on. Well, you can see that here that's, that's 100, and that's 10,000, and that's a million. Oh, it looks like the denominator, every time you go to the next one, you're basically just adding 2 more zeros, right? 2 zeros, 4 zeros, 6 zeros. Well, that's a really nice, interesting pattern, isn't it? It becomes even more interesting when I realize, hey, look, this would keep on going the same way. Oh, well then that is a sum of, well, I don't know, what is it? Well, look, 36 is common to all of these. So let me factor out 36. All right? In fact, here, before I even do that, let me write this as 36 times 1 over 100 plus 1 over 10,000 plus 1 over a million, like that. But now here, we can write this as 36 times, well, 100. 10,000 is just the square of 100. 100 times 100 is 10,000. And then here, that's 100 times 100 times 100. That's 100 to the third power. Just like that. And so forth and so on. So here, this is the sum of 36 times 1 over 100 to the, well, let's see, that's the first power, second power, third power, and so forth. So here that's going to be to the power n, where n goes from 1 to infinity. Just like that, yeah? Oh, but 1, 1 is also 1 to the nth power. Oh, okay, so, if they both have the same power, I can just pull that out. So that's going to be the sum as n goes from 1 to infinity of 36 times 1 over 100 to the power of n. Hey, that's a geometric series, which means it'll converge. Yeah, so, well, it'll converge to a over 1 minus r, which is a fraction. Here, we know a is equal to 36. We know r is equal to 1 over 100, which most certainly has an absolute value less than 1. So this will converge. And not only does it converge, it converges to a over 1 minus r. Okay, so this will converge to, you say, well, no, it won't. It would converge if this was 0. Oh, okay. But we know how to do that. We saw it in the last problem. After all, the sum as n goes from 0 to infinity of 36 times 1 over 100 to the n is equal to, well, notice, that's just the very first term that I need. So that's going to equal to just the very first term. It's going to equal to 36 times 1 over 100 to the 0th power. And then starting from the n equals to 1, I have my sum. N goes from 1 to infinity of 36 times 1 over 100 to the power of n. All right? So here, this is one that's easy for me to find. Notice, from 0 to infinity, well, that's 0. And then from here, I pick up 1, 2, 3, 4, 5, all the way to infinity. So there's only that first term that I don't need. Okay, here's the thing I'm trying to find. I can find this really easily. Anything to the 0 is 1. 1 times 36 is 36. All right, awesome. Here, that's a divided by 1 minus r. So 36 divided by 1 minus r. Plus the sum as n goes from 1 to infinity of 36 times 1 over 100 to the power of n. Oh, but 1 minus 1 over 100, that's 99 over 100. So that's 36 divided by 99 over 100. That's the same as saying times 100 over 99 is equal to 36 plus that stuff there. Just like that. And now I can subtract this 36 from both sides. It's gone. And that gives me that the sum as n goes from 1 to infinity of 36 over, not 36 over, 36 times 1 over 100 to the power of n is equal to 36 times 100 over 99 minus 36. Notice here, 100 over 99, that's the same as 36 times 1 and 1 over 99. 99 over 99 plus 1 over 99 is 100 over 99. But now if I distribute that 36, that's going to be 36 plus 36 over 99 minus 36. These subtract away, and I get a fraction of 36 over 99. In fact, I can even reduce that fraction. The top and bottom both divide by, what will that be, by 9. So here I can write this as 4 over 11. And there it is. This right here is the fractional equivalent. 4 over 11 is the fractional equivalent of 0.36363636. Notice this is not an estimate. By adding the infinite number of fractions that form this decimal, we can find a single fraction, 4 over 11. This is a specific example. Anyone who's feeling a little bit brave, this is not an assignment or anything, but it is something interesting to think about. Anyone who's feeling a little bit brave, there are, try it with a few different numbers. Make up your own repeating numbers, 0.313131, 0.7135, 7135, 7135, 0.44444, whatever. Make up your own repeating numbers and try this a few times and see if you can find a pattern. It actually turns out that there's a very distinct pattern to this. Every time you have a repeating decimal, the fractional versions have something in common, and it's not something that's very hidden. It's something that kind of just stands out. So this is not an assignment, but anyone who's interested in this kind of stuff, sequences, series, or numerical values, numerical approximations, changes in representation, or just someone who wants to challenge themselves, try a few of these and see if you can figure out the pattern. All right, so lastly, for the section, we have a couple of theorems, one of which directly follows from the other. So the first theorem simply states that if you have an infinite series, if the sum as n goes from 1 to infinity of a sub n converges, then the limit as n approaches infinity of a sub n is equal to 0. That's not to say the partial sums. That just means this term right here. If you're going to take the sum of things and have them converge, that means that the individual things should eventually become 0. Now, if you think about that for a minute, intuitively that makes sense. If this doesn't become 0, then you're adding number after number after number. Let's say this converges to the number 1. Well, then eventually you're adding 1 plus 1 plus 1 plus 1 plus 1, which will eventually be infinite. Right? You're adding 1 an infinite number of times. The only way for this to possibly give you a finite number is if these eventually disappear. But sometimes, especially with infinite terms, with infinite number of things, intuition doesn't always work. Fortunately for us, the proof of this one is actually very short and simple. So the proof of this, let's begin by assuming that the sum as n goes from 1 to infinity of a sub n, which is equal to the limit as n approaches infinity of the nth partial sum, right? By definition, this sum is equal to this limit. And let's say that actually does converge. It equals to L, right? So this converges. Okay, so let's assume that that's true. Let's say this thing converges. Well, now consider what happens if you strip off a single term, in fact, the last term of your partial sums. Well, then S sub n is equal to S sub n minus 1 plus A sub n. Here, let's say you had the 10th partial sum. Well, then that's equal to the 9th partial sum plus one more term. All right, that's how partial sums work. If you have one, if you add the next term, that gives you the next one. So if this is s sub n minus 1. Let's say n minus 1 is 50. Okay, you have the 50th partial sum. Well, if you add one more, that's going to give you the next partial sum. That's going to give you s sub n, s sub 51 in my example. Okay, so now notice that the limits of both of these have to be L. Notice that let's write it as a limit. The limit as n approaches infinity of s sub n is equal to L, and the limit as n approaches infinity of s sub n minus 1 is also equal to L. You say, how can they both be L? Well, they're both the same partial sum. Remember, this is just the 50th partial sum, and this is the 49th partial sum. Or this is the 100th partial sum, and this is the 99th partial sum. But whatever, as these approach infinity, this is an infinite partial sum, and this is approaching the infinite partial sum. So this one's doing it a little slower than this one because it's always one term behind, but eventually they'll both approach the same limit. Okay, so here, this is equal to this plus this, but also their limits are the same. So the partial sums are not equal, but their limits are equal. So let's follow the train backwards. Here, if L is equal to the limit as n approaches infinity of s sub n, well, then that's the limit as n approaches infinity of s sub n minus 1 plus a sub n. All right, after all, if s sub n is equal to s sub n minus 1 plus a sub n, then the limit of this one must be the same as the limit of this one. Otherwise, they wouldn't be equal. But we've seen time and time again that limits are linear operations, which means I can apply them separately to each part of my limit. So here, I have the limit as n approaches infinity of s sub n minus 1 plus the limit as n approaches infinity of a sub n. Now remember, I can only do that if both of these converge. Well, they have to converge. They have to equal to L. Okay. So then that means they do converge. So I should be able to split them. But we said just a moment ago, that one's equal to L. This one right here is equal to L. Okay. So then that implies that this very first L is equal to this L plus the limit as n approaches infinity of a sub n. So I can subtract L from both sides. Both of those drop to 0, and I'm left with 0 is equal to the limit as n approaches infinity of a sub n. So that confirms that if you assume that a series converges, then it must be that the nth term eventually goes to 0. And that concludes our proof. By inverting this statement, we get our next theorem, our last theorem. Here it says if this converges, then this is equal to 0. So what if this was not equal to 0? Well, if this converges, this has to be equal to 0. So if that's not equal to 0, well, then it must be that this one didn't converge. Oh, okay. So that's called the nth term test. And it follows directly from our previous theorem. The statement follows directly from our previous theorem. This is called the nth term test. And it simply states if the limit as n approaches infinity of a sub n is not equal to 0, then that means that the sum as n goes from 1 to infinity of a sub n must diverge. If this converges, then this limit's equal to 0. So what if this limit's not equal to 0? Well, then it must not have been that this converged. So here, if this is not 0, then this does not converge. Oh, so if this is not equal to 0, then this does not converge. Oh, so then it diverges. All right. Here, we don't really need to prove that. That really follows directly from the previous statement. Proof follows as a consequence of the previous proof, of the previous theorem, really. All right. Note one thing. If this is not equal to 0, then this diverges. If this is equal to 0, we have no idea. Sometimes the nth term will go to 0, and this will converge. Sometimes the nth term will not go to, sometimes the nth term will go to 0, and this will converge. Sometimes the nth term will go to 0, and this will not converge. If this goes to 0, we have no idea what happens here. If this doesn't go to 0, we know for a fact it diverges. So here, note the nth term test can only prove divergence. It cannot prove convergence. If you ever say, oh, I know this series converges because of the nth term test, that's wrong. There's no way it can ever do that. The nth term test can only tell you it diverges. All right? There will be some times when this limit is equal to 0 and this will converge. And there will be other times when this is equal to 0 and this will diverge. You can never tell. You can only prove divergence. So, as a nice example, let's consider the question, does the series converge or diverge? This will be a common question in coming sections. Up to now, you've been asked, what does it converge to? What is this sum equal to? That is going to be many times not possible, or at the very least not simple to find. Many times the question will simply be, does it converge or not? If it doesn't converge, if it diverges, if it doesn't converge, well, then you're done. If it does converge, well, then maybe you're going to want to try to estimate what it converges to, or maybe not. Or maybe we can find some clever way of finding out what it does converge to, or maybe not. But this is often the first question. All right. So does the series converge? Let's take the sum as n goes from 1 to infinity. Incidentally, here the nth term test talks about a series, a series from 1 to infinity. This doesn't have to be 1. The nth term test really works for any starting value. It could be n equals to 0, n equals to 1, n equals to a million. Because, of course, if this is an infinite series, if you cut off the first term or the first 10 terms or the first million terms, who cares? What matters is what happens as you approach infinity. So here, if I had said n equals to 5 instead of 1, this will still work just fine. So let's see, the sum as n goes from 1 to infinity of 4n plus 1 over 3n minus 5. We'll consider the nth term. Let's consider the limit as n approaches infinity of a sub n. That's going to equal to the limit as n approaches infinity of, well, a sub n is the nth term of my series. So 4n plus 1 over 3n minus 5. Notice this isn't a partial sum. It has nothing to do with a sum. It's just the nth term, hence the name, the nth term test. So here, this will test whether or not the series will converge or diverge here. So let's see here. This one is, well, if I divide everything out by n, I get 4 plus 1 over n over 3 minus 5 over n. Or if you prefer, you can think about this as a continuous case and then use L'Hopital's rule. Either way, you end up with 4/3. Which, of course, 4/3 is definitely not 0. So by the nth term test, since the nth term does not go to 0, that means our series diverges. Okay. Now, again, be very careful about the opposite direction. Same kind of question. Sum as n goes from 1 to infinity of 1 over n. This, incidentally, in a coming section, this will be called the harmonic series. It's a particular series. But for now, it's a series. And the question, does this converge or diverge? Well, right now, let's say we're trying to use the nth term test. Let's take the limit as n approaches infinity of the nth term. Well, that's going to be the limit as n approaches infinity of 1 over n. And that one's nice and simple. As n approaches infinity, this becomes an infinitely big, which means 1 over something infinitely big tends to 0. This does not mean your series converges. It means the nth term test fails. When we say a test fails, that means we learned nothing. We don't know if this converges or not. Likewise, let's say we were to look at the sum as n goes from 1 to infinity of 1 over n squared. Well, again, using the nth term test would not really yield any results, because this would be the limit as n approaches infinity of 1 over n squared, which again is 0. Here the nth term test fails. Incidentally, in both of these cases, the nth term goes to 0. You'll see in a later section, this diverges, this converges. So that means the nth term test doesn't discriminate between those, which means it fails. It doesn't tell you enough information. So note, the nth term test can tell you whether or not something diverges, but it never really can tell you if it converges or not. Here, oh, that's not 0. I know it diverges. Done. This is equal to 0. I have no idea. Right, so that is it for our section. As an assignment for the section, you should try section 9.2, exercises 5 through 57, every other odd, meaning every fourth problem, number 5, the number 9, the number 13, and so forth. Also try numbers 61 and 63. They are a reasonably accessible version of something that we'll be looking at in much more detail in later sections. So this is the end of our section, and I hope you all have a good night.